Okay, so today we're still going to be talking about some calculus, and then I'm going to kind of tell you what a lot of these definitions actually mean to me, and so I can figure out some of the things that I've gotten wrong on. I don't know, that just sounded weird, but first we're going to start with the epsilon delta definition. So it goes like this. So for every, for example, let's say we have like lim when x approaches a, fx is going to be equal to L. And this means that for every epsilon that's greater than 0, there always exists a delta to make, there always exists a delta where if x minus a is less than delta, then fx minus L is less than epsilon. So what this is saying is that, like, given, for example, let's say, given a graph, right? And then, let's say approaches here. And so as long as we can control the kind of imprecision within a certain range, we can always guarantee another imprecision. This is what basically limits are saying. However, you're still going to think that, well, imprecision is just very, very vague. It's not that much better than the definition, but the original definition, but at least right now we have something that we can kind of apply mathematical language to. And so this is pretty important. And so you're also going to come across something like infinite limits. So for example, lim when x approaches infinity, fx is going to be equal to L. What this means is that, so for every, let's say, how about we make this easier? When x approaches a, we're going to get this to infinity. So for all, okay, we're going to change it to this. So for all m that's greater than 0, there always exists an n greater than 0 to make if x is greater than n, then fx is greater than m. That's something that always exists. And then there's also something. Okay, so going back to what I said is that if lim x approaches, let's say, infinity, and then fx is going to be equal to L, this basically means that for every epsilon greater than 0, there always exists an n. So for if x is greater than n, then fx minus L is going to be less than epsilon. So this basically means that when x approaches infinity, basically is something like this. Let me draw this. So for example, it's like that. So for every x is that you're getting x more and more over here, and then it always the imprecision is always contained within a certain range. That's all that it means. And we can also say that, for example, limit, why did I write limit? But lim when x approaches a, fx is going to be equal to negative infinity. This means that for every, let's say, for every m, there always exists a delta that's less than, there always exists a delta that's greater than 0. And then if x is less than m, and then we get is, so if x minus a is less than delta, then we always get fx is, then we always get fx is, so this is kind of weird. we always get fx is less than m, basically. Yes. So, yeah, I guess. So for every n is basically, so for every n there always exists. Yes. Okay, good. And then this is basically all the infinite limits. I'm still getting kind of shaky with the infinite limits, but I think it would be good if I put a little bit more time into understanding this. But infinite limits are pretty important to like kind of come across. And then something else I came across today is like the intermediate value theorem, is that there are two like conditions that you need to apply to intermediate. First of all, it needs to be continuous on the interval like a and b. It should be continuous like on here. And then the n must be within fa and fb. So it can't just be random n. And so it's just that you're going to try to control the imprecision and try to make it work. And so a question today that I haven't solved would be like, what does m and n actually stand for, and why did they give it m and n? Because it's kind of weird. Why? And that's basically infinite limits. And what else is there today that I haven't talked about? There could also be, for example, yeah, the rest is basically me doing problems. And there are some like interesting problems. For example, if you see like irrational equation on the top, for example, like, I don't know, let's give it like, let's say t squared plus 9 minus 3 t squared. And I'm trying to find the limit when t approaches 0. So I was getting kind of stuck on here because I didn't really know what to do. But it turns out you can actually do this. You multiply the top and the bottom by plus 3, so it turns into t squared, and then t squared, what is it, t squared plus 9 plus 3. Okay, the parentheses, and then we cancel these out, and then it's just going to be equal to t squared plus 9 plus 3 over 1. Oh, so this is going to be, when x approaches 0, this is going to be 1 over 6. And so something really important that is that if it gives you a limit that you can't really do, you just rationalize it. Yes. Yeah.